In this set of notes, we're going to look more at Poisson regression. And so what we looked at in the last module was just the basic structure of Poisson regression, and you saw that it was very similar to logistic regression. There were some slight changes that needed to be made since we were working with the Poisson distribution instead of the binomial, but the overall structure was pretty much the same. Now, there are certain concerns with Poisson regression that may come up that we need to modify that most basic of models. And two of the biggest concerns that you're going to see are that the mean and the variance for the Poisson distribution are the same. And sometimes when we're modeling an outcome that is counts, if we look at those counts, it ends up that the mean and the variance of the observed counts, they aren't even close to being equal to one another. So modeling, with the most basic of Poisson models may not be the best choice. The other issue is that when we think of the Poisson distribution and its parameter lambda, it's the rate parameter. And so often when we think of a rate, the rate is usually per something. And so we may want to account for that as well in the Poisson distribution or the Poisson model. Now, the third one that we're not going to talk about in this note set, but you are going to look at for the additional reading this week, is that sometimes you end up with what's called zero inflation. And so depending on the outcome variable, it may be that very naturally that outcome variable has a large number of zeros, and then the rest of the counts look very similar to a Poisson distribution. And so that's what we call a zero inflation. And so we'll talk again, or you'll look at in the additional readings for this week, what we can do when we have zero inflation. All right, but we are going to start out by first looking at the rates. So the meaning of lambda often requires additional thought. And so when we use a Poisson model, what we're modeling is the rate of events. And so we want to be very careful when we think about what is it that we're actually trying to estimate. In other words, a rate per what. And so, for example, if we were modeling motor vehicle crashes, we may be estimating a rate per 1,000 people, or a rate per 1,000 licensed drivers, or 1,000 registered motor vehicles, or per 100,000 miles traveled. And so, since lambda is a rate, we need to think about how we incorporate that information into our model. And this is where that idea of offsets comes into play. And so let's start out by looking at the British doctor study. So a kind of rate that is particularly common, especially in epidemiological studies, is a rate per person years of follow-up. So for consider, there was a classic study by Dole, which all British male doctors were sent a questionnaire about their age and whether they smoked tobacco. The doctors were then followed up for a number of years to see whether or not they had died from coronary heart disease. And so this is what the actual data set looks like. So notice first we have ages in groups, we have smoking status, the number of deaths, and then we also have person years. So notice that each of these rows don't represent a single person. They really represent a group of people that have been combined into person years. And so again, looking at age and smoker, for example, we have 35 to 44 and smoker, but then also notice down here you have the corresponding non-smoker groups. And then obviously in terms of deaths, we do see a lot more deaths in the smoker group than we do the non-smoker, but of course we always need to account for, out of actually how many. So in this case, in person years, we see that we had 18,000 in the non-smoker, but 52,000 in the smoker. And so we need to account for that when we think of these rates. And we also need to decide, well, a rate per how many person years. And so, for example, suppose that we wanted to model lambda as a rate per 1,000 person years of follow-up, giving the explanatory variables age and smoking. And so what we would end up is that when we think of the expected value of the expected value of y, it's not lambda, it's actually going to be ti times lambda. And the reason for that is that for this particular example, ti is going to be equal to person years I divided by 1,000. And so notice for each of these rows, we'd have a different person years I. And again, since we want that as a rate per 1,000, really what we're doing here is we're dividing by that 1,000. And so again, TI is going to denote the person years of follow-up for observation I. And so this is going to imply the following. So notice here, we have that log mu, where mu I is our mean of our distribution. That's really going to be equal to log of ti plus log of lambda I. So that's coming from when we use mu to denote the mean here, that mu is equal to ti times lambda I. In other words, exactly what we have right here. And then, of course, if I use the property of logarithms and take the log of both sides, I end up with the following. But notice what we end up with here is we have the log of ti plus nu I, where nu I is what we saw last time in terms of a Poisson regression model. So that usual relationship between mu I and that linear predictor is offset by the amount log ti. In other words, it's offset by this piece right here. And so that's why we call it an offset. So even though really what we're doing with an offset is we're defining what that rate is in terms of, and we're controlling for that. The reason it's called an offset is when we look at the log of the mean, we see that it's offset by this particular piece. And remember, we're using the log here because that was the canonical length that we saw before. All right, so you can include offsets in both R and SAS. In SAS, you simply add the option offset equal to. So in SAS, it's very, very straightforward. Similarly, in R, you specify the offset equals option as well inside the GLM function. Now, one thing that you do have to be careful about is in SAS, you can't just take, okay, this is my explanatory variable and I want to divide it by this, and when you do the offset, you have to make that transformation in a separate data step and then use that new variable when you go to actually fit your model. Whereas in R, you can actually do that transformation within the GLM. So for example, when you would fit GLM, when you set offset equal to, you can actually include that log function inside of the GLM function. So that's really the only two differences between SAS and R. And that's a pretty common difference between the two of them. In general, in the different procedures in SAS, you can't have that function inside of it. We typically will do a data step beforehand where we transform the variable and then use that new transformed variable inside of the actual procedure call. All right, so here, notice what we're doing here is just some example R code. Here we're naming PY is equal to that person years divided by 1,000, and then in the actual GLM we call offset is equal to log PY. Again, instead of defining PY separately here inside the log function, I could have had doctor's $ person years divided by 1,000. That would have also been perfectly fine. You do have to be a little bit careful when you do that though, because since we have defined that we're using the doctor's data set, you could probably just have person years divided by 1,000. You always want to be careful with that with any GLM or LM. If you're calling the data set in there, you don't need to recall the data set or vice versa. All right, and so then here is the output that we get. Again, just as we would normally expect, the format of the output looks very similar. Here we have all of our estimates. We've got the number of iterations, what we would usually expect to see. All right, so we can now then estimate the rate per 1,000 years of follow-up for any category we choose using the estimate statement in SAS or the predict function in R, similar to what we've seen before. So for example, with SAS's default coding of class variables, the following statement estimates the rate of CHD deaths for smokers age 45 to 55. And so here we've seen things like this in the linear regression course. Here you've got the estimate for the 45 to 50-year-old smokers, and then we've defined what that looks like. And notice what we've got here is we've got our two different explanatory variables, and we just have to remember in SAS, how those orders, the different categories, how they are ordered, that's how you have, your zeros and your 1 here. So 45 to 54 was the second category for smokers, so that's why you see the 1 there. And then if we went for smokers, it was non-smokers were 0 and smokers was 1. And so in R, we can set up a data frame consisting of all the linear combinations we're interested in, and then submit the predict function. So one thing to note here is that in SAS, the offset is set to 0. In R, you specify the offset variable. All right, so next we're going to look at, oops, fix my page here. We're going to look at the additive model. And so here, pretty much just like you've seen before, I'm using R. We're fitting that additive model. And then if we come down here, here are the different estimated rates for the Poisson regression model. And again, these are coming from up here. And so by fitting the model with no interaction between age and smoking, we enforce that the rate ratio between smokers and non-smokers are the same in each group. And so you can go through and check that here. So, but in other words, this is very similar to what you saw in the last set of notes. It's just that by setting that offset, we can now interpret everything in terms of rate per 1,000, whereas before we wouldn't be able to do that. And that's really all the offset is allowing us to do. And so you could define your offset for whatever reason you wanted it rate per 5,000 person years. You could do that as well. So the offset is really just allowing you to tweak in your interpretation what that rate is for. And then here's what the interaction model would look like. And so again, here's the estimated rates from our Poisson regression model. And so it's an adequate tool for analyzing cohort studies. However, if one has detailed individual level data, you can apply the more sophisticated approaches that have been developed in this field of a survival analysis. And so that's kind of more of a note, outside of this course, but if you haven't taken a survival analysis course, you could take one, and if you had that individual level data, you could do even more. All right, so next we're going to look at over dispersion. And so again, one of the defining characteristics of the Poisson distribution is that the mean is equal to the variance. And there's no parameter in the Poisson distribution that allows us to adjust that relationship. So in practice, when working with Poisson regression, it's often the case that the variability of that outcome variable is larger than what we're actually going to predict. And this implies that there's more variability around the model's fitted values than is consistent with the Poisson distribution. And so this phenomenon is called overdispersion. And so data for which this phenomenon manifests itself are often called overdispersed, although what we're going to see, it's probably better just to refer to the model as being overdispersed and not the actual data. And so it ends up there are two common approaches for correcting overdispersion. There's what's called the Quasi-Likelihood Approach, and then there's the negative binomial approach. And we're going to briefly look at both of these. So starting out, recall that previously we saw the score function for the Poisson regression model, and here's what that looks like. And in this particular case, theta is equal to log lambda. Remember, that's our canonical parameter. And so, of course, there's no scale parameter which would show up in the denominator on the right-hand side. And so if you remember when we think of that scale parameter, that was back when we were looking at the exponential family. But let's add one in to the denominator. And so recall that if we look at the variance of y, that is equal to phi times the variance of mu. And so if we define it this way, we have a parameter that allows the variance to be larger or smaller than the mean by a multiplicative factor. And this is not going to change our beta hats, but it will affect inference, since if we look at that asymptotic distribution, we're going to have the following. And so remember, before we had this placed out front, but we kind of ignored it because we knew that it was 1 for a lot of the distributions we work with, so like the Poisson. But here we're saying, well, what if we just put that parameter in and we see what happens? And so notice what is really this is going to do is when we look at that asymptotic distribution of beta hat, our estimate of beta hat stays the same. Oops, sorry, I didn't mean to mark that out. the estimate itself stays the same, but the variability of the estimate is now going to change. And so the question here is, well, what distribution is this actually? And the answer, it isn't one, or at least not one that you can write in closed form. So this is an approach where what you're doing is, instead of modifying the distribution that we work with, you're modifying the score directly. And so you never actually specify a distribution here, and that's why it's called quasi-likelihood, because you don't have an actual distribution, you just modify the score function directly. And so typically that scale parameter is estimated using the method of moments estimator. This is what that would look like, where chi-square is the chi-square statistic, n is the sample size, and p is the number of parameters including the intercept. So to use this approach in R, you can specify, instead of family equal Poisson, you do quasi-Poisson. And in SAS, one can do the p-scale option in the model statement. And this is often called the dispersion parameter. And so this was what this would look like for the Belgian data AIDS example. So again, first thing we're going to do is we are going to plot this in R, and here's what that plot would look like. And then, so for illustration, we're now going to calculate the estimate of that dispersion parameter doing the following. So first, to estimate the dispersion family parameter, we're going to do our normal fit where we have GLM, and notice that family is equal to Poisson. And then here what we're going to do is we're going to look at the sum of the residuals. So in other words, what we're doing here, we're looking at that chi-squared. And then again, we're going to fit here's the output, and here we have the sum of those residuals squared. Oops. So next, if we fit the model with the over dispersion, notice here now we're going to have family equals quasi-Poisson. And then we have that summary here for the quasi-Poisson, and that is down here. All right, and so here is the comparison of a plot of the two different fits where we have the number of cases on the y-axis and year on the x-axis. And it ends up that for the Belgian data, we can see that phi hat is 6.7, implying that the variance was nearly 7 times larger than that implied by the Poisson distribution. So again, the fit is the same, so the blue line between the two is the same, but our standard errors are about 2.6 times bigger. And we can see that by looking at the error bars on the two different lines. And so again, when we think of accounting for this over dispersion, or using an over dispersion model, the quasi-likelihood, again, we're not changing the estimates, it's really that variability is what we're accounting for. Now it ends up that the quasi-Poisson approach is attractive for several reasons, but its big drawback is that it lacks a log likelihood. And so this is going to prevent you from using any of the likelihood-based tools we've discussed for GLMs. So things like likelihood ratio test, AIC and BIC, deviance, explain, deviance residuals. And so there is an alternative approach that allows all these maximum likelihood tools, and it's based on the negative binomial distribution. Now the negative binomial distribution has other uses in probability statistics. We saw the negative binomial in 675, but for our purposes we can think about it as arising from a two-stage hierarchical process. And so how this works is we can think of Z is distributed gamma, where the two parameters in the gamma distribution are equal to one another, and then conditional on given Z, Y is distributed Poisson, where the rate of that Poisson distribution is lambda times Z. And it ends up that the marginal distribution of Y is a negative binomial, where the expected value of Y is equal to lambda, and the variance of Y is equal to lambda plus lambda squared divided by theta. So then, like the Poisson distribution, the negative binomial has support over only the positive integers, but unlike the Poisson, its variance is going to be much larger than the mean, and we can actually see that right here because we end up with that additional term here in the variance of Y. Now, this still isn't a perfect solution because the negative binomial is not a member of the exponential family. Thus, the theory and fitting procedures we've developed for GLM, they're not going to directly apply. And it ends up, for this example, there's no canonical link. However, it's customary to employ a log link to make the negative binomial regression look like Poisson regression. So, regardless, in GenMod and SAS allows for the choice of distribution equals NB for negative binomial, and in R you actually have to use the glm.mb function, and it's located in the mass package. So again, the big takeaway here between the quasi-likelihood and the negative binomial distribution, each of them are over dispersion models. And so in other words, they're allowing us to account for this fact that we may not have the variance be equal to the mean, but neither of them are perfect solutions. So when we look at the quasi-likelihood, since really we're just modifying the score function and not having an actual distribution, we can't use any of the likelihood things that we've seen. But if we use the negative binomial approach, we can define that distribution, but it ends up that distribution isn't part of the exponential family. And so for that reason, we can't do a lot of the things that we already saw with GLMs. We can't find a canonical link. We can't do some of those nice things that we saw previously. So for the Belgian AIDS example, it ends up that theta hat is equal to 19.2, implying the following mean variance relationship that you can see right here. And so this leads to the following comparison between the three different methods. So if we just fit, your regular, plain Poisson regression, this is the quasi-Poisson, and then this one is the negative binomial. Again, in all three cases, our actual estimates are the same between these two, but we can see that especially the quasi-Poisson and the negative binomial, they are giving much wider error bars. And so arguably the negative binomial estimates are even worse than the Poisson estimates, and certainly drastically worse than the quasi-Poisson model. However, its goodness of fit is much better. And so this is why it was marked earlier that it's wrong to think of the data as over-dispersed if the models show more variability than the model can explain. The most likely explanation is a bad model. The quadratic Poisson fit shows no over-dispersion. The residuals are actually slightly under-dispersed. And accounting for over-dispersion is a good idea if the model doesn't fit the data. This should be reflected with larger standard errors and wider confidence intervals. However, many analysts have the view that quasi-Poisson or negative binomial regression automatically fixes the over-dispersion problem. This is a potentially dangerous misconception, surely accurately modeling the mean of greater priority than modeling the variance. And so this is, again, going back to that. We always want to be critically thinking about, what it is that we're doing. Again, going back to these three, between the Poisson and the quasi-Poisson, we end up with the same estimates, but the quasi-Poisson is better, modeling those errors. But if we look at the negative binomial estimates, it doesn't fit as well. It's similar, but it's not as good of a fit, but we do get that wider error bar. And so what that bullet point is saying is, yes, quasi-Poisson and negative binomial are going to do a much better job when it comes to estimating those standard errors that are associated with our estimate. But if the estimates themselves aren't as good, does that really matter? And so this goes back to that idea of, really we have, two things that we're interested in. We want to make sure that we can estimate, our parameters, or in this case, we look at our model fit. We want that to be good, those estimates. But we also want good standard errors. And so it's going to be a balance between those two. And in this case, neither of these are perfect solutions, so we don't want to always think that, this is a magic fix. We just always want to do this. We want to think critically about what it is we're doing, always looking at our plots, and really making sure, that trade-off is it an appropriate trade-off. And then while quasi-Poisson and negative binomial approaches are useful, they are certainly no substitute for careful consideration of the systematic component of the model. And so in either case here, let's say we had additional explanatory variables that we wanted to use, or maybe ones that we left out, or, let's say there was a quantitative variable in there, we should have considered a quadratic term. All of those are very important considerations when we think of that systematic component. And so if our systematic component is not good, quasi-Poisson and negative binomial are not going to fix that. So, always going back and thinking about our systematic component. Are we, have we included everything we should? Have we maybe included things that we shouldn't have? Those are pieces that we can't forget about, and we need to make sure that we really understand what is going on there first, as well as thinking about accounting for, having a model that accounts for over dispersion.